The strength of the bonds and intermolecular forces affects the heat of fusion, heat of vaporization, vapor pressure, and phases. This shows the changes of state. So here we start as a solid, where as you increase the heat, you increase the temperature. During this part, which is the heat of fusion, it's converting from a solid into a liquid. So it's staying at the same temperature, even as you're adding heat, until all of it has liquefied. Then this is the liquid state as you increase again. Then this is the heat of vaporization, during which it's converting from a liquid to a gas and staying at the same temperature. And then it's increasing up to a superheated gas. You know that solids are held together in a regular pattern by intermolecular forces, the electrostatic attraction of the positives to the negatives. In this one, you can see the dipole-dipole is drawn, and there's also London dispersion forces. Fusion may make you think that it's turning from a liquid into a solid, but the heat of fusion is actually defined as the heat gained as 1 mole of a solid liquefies. The same intermolecular forces exist in liquid and solid phases, however they're not as strong in the liquid phase. But the liquid phase is much stronger than in the gas phase. Ideal gases wouldn't experience any intermolecular forces. In a gas, we generally assume that particles have no intermolecular forces. In a liquid, attractive forces are still quite large. The heat of vaporization is the heat required to go from a liquid to a gas. Vapor pressure is the pressure that is exerted as the molecules leave the surface of the liquid to enter the gas phase. It depends on how much surface area you have. We looked at this when we looked at collecting gases over water. Vapor pressure and equilibrium. In a closed container, a liquid will reach a state of equilibrium where the rate of evaporation equals the rate of condensation. We'll learn more about equilibrium in the next unit. A phase diagram describes the state of matter exhibited by a substance under different conditions of pressure and temperature inside the apparatus. Phase diagrams do not describe the states of matter that exist under normal atmospheric conditions, nor do they describe the conditions that would exist in an open system. Phase diagrams only describe the states of matter that exist within a closed cylinder under very specific conditions of pressure and temperature. All phase diagrams are plots of temperature versus pressure. The pressure is the pressure inside the cylinder, and the temperature is the temperature inside the cylinder as well. We're going to look at phase diagrams that consist of 3 lines. At any point on this line, liquid and gas exist in equilibrium with one another. This could be considered the boiling point curve, as water only boils on the points that fall on this line. Liquids and gas only coexist within the cylinder on this line. So this is the point where it's going through the phase change from liquid to gas. Above the line is only liquid, and below the line there's only gas. In an open system, water would boil at every point along this line. Solids and liquids coexist in equilibrium with one another within the cylinder at any point along this blue line. Increasing the temperature from any point on the blue line will give you only liquid. Decreasing the temperature will give you only ice. Increasing the pressure from any point on the blue line will give you only liquid. This is because solid water is less dense than liquid water. Ice floats on water, which means that it's less dense. When you increase the pressure on the ice, it attempts to reduce that pressure by increasing its density. As you can see from the graph, you have liquid water at temperatures below 0 degrees Celsius if the pressure is above 1 atmosphere. That's what gives the solid-liquid equilibrium line, this line right here, a negative slope. The green line is a sublimation curve. It shows the relationship between solid and gas. To the left would be only ice, and to the right would be only gas. Liquids cannot exist along this line. The triple point is the place where solid, liquid, and gas can all exist at the same time. For water, the triple point occurs at 0.006 atmospheres and 0.0098 degrees Celsius. This occurs because both ice and liquid water have identical vapor pressures at this point. The triple point is the only condition of pressure and temperature where a substance can exist as a solid, liquid, and gas. The 3 phases maintain a state of equilibrium with one another. This occurs because both ice and liquid water have identical vapor pressures at this point. The critical point is the point at which it's impossible to distinguish between liquids and gases. For water, this occurs when the pressure is greater than 218 atmospheres and the temperature is greater than 374 degrees Celsius. As you continue to heat the substance in a closed container, the concentration of gas increases as more gas evaporates. That causes the density of the gas to increase. As a liquid absorbs heat, its density decreases. When you reach the critical point, the density of the gas and the density of the liquid are equal to each other. At temperatures above the critical point, you can't get water vapor to liquefy even if you go with a pressure higher than 400. And at pressures above 218, you can't get the liquid water to vaporize. So it becomes a supercritical fluid. It's called superheated gas. It's not really a liquid and it's not really a gas. So here's the phase diagram of CO2. Now this solid-liquid line has a positive slope, which is much more common. Anything where the solid has a greater density than the liquid is going to have a positive slope. This line is the line of sublimation. You've seen dry ice, and when you leave it out, it goes straight from a solid to a gas. Liquid carbon dioxide can't exist at 1 atmospheric pressure. So here's 1 atmospheric pressure. You don't have any liquid. It's right on that sublimation line. That's the pressure that we're normally at. So here's an example. Describe the phase changes that occur if CO2 is kept at negative 52 degrees Celsius, while the pressure increases from 1 atmosphere to 50 atmospheres. The first step is from 1 atmosphere to a little over 5 atmospheres, there's only carbon dioxide gas in the cylinder. Step 2, the liquid forms when the pressure is a little greater than 5 atmospheres. The liquid that is formed is boiling. Liquid and gas are at equilibrium at this point. The vapor pressure of the gas is equal to the pressure in the cylinder. Step 3, as the pressure increases a little, the boiling stops and only liquid is present in the cylinder. Step 4, some solid forms, and solid and liquid exist together in equilibrium. And step 5, when the pressure increases a little bit past this point, all of the liquid solidifies and there's only solid in the cylinder. When 50 atmospheres is reached, the cylinder still contains only solid CO2. What you need to be able to do with phase diagrams is you need to be able to draw them, identify the critical point, and identify the triple point. One other topic related to bonding that I want to throw in here is dative or coordinated compounds. An example is BF3. You know that that's an exception where there's no electrons here on the boron. Now this makes it very reactive because it can accept an extra pair, because if you have ammonium has this extra pair. So this is going to bond to this boron to form a coordinated complex. Boron in this state by itself with BF3 is not very stable because it has that empty spot where it doesn't have the full octet. So this is going to form so that it's much more stable. And that's it for bonding, so we're just going to be practicing much more, and I will see y'all later.